Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. In continuation of our online presentation, CHM 155 Polymer Chemistry, today we'll be discussing about condensation polymerization, Chapter 8. Chapter 8 will be divided into two. We're going to discuss Part A, and then the next lecture is going to be Part B. So we start with 8.1, which is the functionality of the monomers. Now, when we talk about functionality, functionality is the number of reactive center on a monomer, or how many bonds, the number of chemical bonds that can be formed by a monomer during polymerization. We should understand that not all substances can be polymerized. For example, you remember when we talk about alkane in chapter 1, we said alkane cannot form polymers directly. We have to convert alkane to alkene, double bond, before we can do polymerization. And this is achieved in the industry through cracking. Now, for a monomer to be converted into a polymer, the functionality must be greater than or equals to 2. Now, when we say functionality, as I said, is the number of reactive center. For example, if you look at ethylene, ethylene can form a bond on this carbon, it can form a bond on this carbon. So it means that the functionality of ethylene is equals to what? 2. So which means that ethylene can combine with another ethylene monomer to form a polymer, because we said for a monomer to form a polymer, the functionality must be equal or greater than 2. So if you have one double bond, it means that the functionality is equals to 2. Now, if you look at this monomer, in which X is represented, X could be hydrogen, it could be chlorine, it could be methyl, it could be hydroxyl, it could be benzene ring. If it is hydrogen, then we say it is ethylene. If it is chlorine, it's vinyl chloride. If it is methyl, it is propylene. And if it is OH, it is vinyl alcohol. If it is benzene ring, then it is called styrene. Since all these monomers will react on the double bond, it means it has one double bond, it means the functionality is equal to 2. So for each double bond, functionality is equals to 2. Now, if you look at the second monomer here, this is butadiene. It has 2 double bonds, which means that the functionality is equals to what? 4. Remember that if you have one double bond, functionality is equals to 2. If you have 2 double bond, functionality is equals to 4. Now, if you look at this one, this compound has benzene ring. So if we are counting the double bond, the benzene ring is not involved in the reaction. So we count the double bond, this double bond, and this double bond. So this one has 2 double bonds, two double bond, one here, and this is the second one. So if you have 2 double bond, it means that the functionality is equals to 2. Now, as I said earlier, that for polymerization, functionality must be greater than or equals to 2. This monomer can form a polymer, this can form a polymer because its functionality is 4. This one can also form a polymer. Now, you remember that we talk about classification of polymer based on reaction, polymerization reaction. It could be reaction of multiple bond, which is in most cases double bond, and reaction of functional group. So for a double reaction of a double bond, each double bond has functionality equals to 2. One double bond means functionality equals to 2. 2 double bond means functionality equals to 4. 3 double bond means functionality is equals to 6. We can also define functionality in terms of functional group. And this one is very straightforward because the functionality is equal to the number of functional group. So if a molecule has one functional group, it means functionality is equals to 1. If it has 2 functional group, it means functionality is equals to 2. So let's look at this example. This is terephthalic acid. It has 2 functional group. It has carboxylic acid group here and another carboxylic acid group here. so the functionality is equals to 2. If you look at this this molecule, it has two functional group, one alcohol and one carboxylic acid group, so it means the functionality is equals to 2. If you look at this one has only one carboxylic acid group, so it means the functionality is equals to 1. If you look at this one has two group, diamine, one amine here, one amine here, so the functionality is equals to 2. So functionality in terms of functional group is the number of functional group. Now the last one here has 3 functional groups, 3 alcohol group, OH, 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 1, 2, 3. So it means the functionality is equals to 3. So functionality can be defined in terms of a double bond, carbon-carbon double bond. If you have one carbon-carbon double bond, the functionality is equals to 2. If you have 2 carbon-carbon double bond, functionality equals to 4. But in terms of functional group, the functionality is equal to the number of functional group. One functional group means one functionality. 2 functional group means 2 functionality. And then it continues. Now, if you look at the next one, we can also have functionality. This is our special cases. These ones are determined by experimentally determined. The first one is based on the carbon-carbon double bond. The second example we'll look at is based on the functional group, but this one is based on experimental determination. For example, this is a phenol. Phenol was discovered to react at this point, at this point, at this point. So these 3 points, you have 1, 2, 3, it means the functionality is equals to what? 3. Even though it has one functional group, which is alcohol group, we don't count the number of functional group here, we count the number, the reactive center. At what point this molecule will form a bond. It forms a bond at this point, at this point, and at this point. So the functionality is equals to 3. For these special cases, you just have to remember their functionality. Another special case is formaldehyde. Formaldehyde was discovered to react at this point and at this point. Star means reactive center. The center at point where it will form a bond. So the functionality here are 2 functionality. Another example, special case we are going to consider in this polymer chemistry course is phosgene. Phosgene was previously used for the production of polycarbonates. It was also discovered to react at this point and at this point. So you have star here, so it means the functionality is equal to 2. So in this course, we are going to encounter only 3 special cases: phenol, formaldehyde, phosgene. For this, there is no specific rule. They are called special cases, and we need to just remember their functionality. For example, phenol functionality is equal to 3, formaldehyde functionality is equal to 2, and phosgene functionality is equal to 2 also. Now, this functionality will determine whether a particular reaction will produce a polymer or not. So let's look at 8.2. 8.2 talks about condensation reaction. Condensation reaction is the reaction in which 2 monomers will react to give a molecule and to eliminate what? Water. So in this reaction, water is eliminated. So you have, if you look at this is ethanoic acid. The functionality is 1 because it has acid group. So the organic acid group, the functionality is equals to 1. This one has ethyl alcohol. It has 1 alcoholic group, so the functionality is equals to 1. So it means that if you combine a molecule with functionality is equals to 1 with another molecule with functionality equals to 1, there is going to be a reaction, but that reaction will not produce a polymer. So what happens is the the OH from the hydrogen from here, from the OH from here and hydrogen from alcohol will be eliminated to form what? Water. Now that is why it is called condensation condensation reaction. So if you remove this OH with hydrogen here, then this unit, the remaining unit here, will combine with this to give what? Ethyl acetate. So this is from the first part, and this O here, CH2CH3, or CH2CH3 will combine to form this with the elimination of water. So if you look at this product, there is no functional group at the end here. There's no functional group, so there is not going to be any further reaction. So no polymer is formed, and the reaction is called condensation reaction because small molecule is eliminated during the reaction. And this reaction is what? One-step reaction because it is just a combination of A and B to give what? Ethyl acetate. Ethyl acetate cannot react further because it has no terminal functional group. So when you look at it, there's no functional group at this end, there's no functional group at this end. So in that case, we say no polymerization, and the reaction is called condensation reaction. So in summary, if you have functionality is equals to 1 plus functionality is equals to 1, no polymerization. Now let's look at the second case where we have F is equals to 1. It means that it has one functional group, which is carboxylic acid, and here you have F is equals to 2, which is ethylene glycol. Ethylene glycol has two alcohol functional group. We have OH and OH. So this functional, because you have two of these, it means that the functionality is equals to 2. So let's look at this situation. We have functionality equals to 1 plus functionality equals to 2. So this is also this will also undergo condensation reaction, which means the elimination of water molecule. So you eliminate water molecule from, in most cases, hydrogen is taken from the acid and OH from alcohol to form water. So this unit and this unit will combine together to give another ester group. But this time we have one alcohol group at the end. So which means that this monoester is still active. It can undergo another condensation reaction. So this unit, which is monoester, will combine with another ethanoic acid. This is the monoester, and then you have ethanoic acid from here. They combine together, and they also undergo condensation reaction where OH and H is hydrogen and OH is eliminated as water to form diester. So now you have two ester group, but at this end no functional group, at this end no functional group. So the reaction will stop, no further reaction, and because of that we say no polymer, because polymer should be a molecule that has long chain, but this one is just 2 units. And the reaction is also called condensation reaction. But let's look at the next condition, which is 8.3, condensation polymerization. That is condensation reaction that will lead to a polymer. Now, the first here example here, we have diacid here. The functionality is equals to 2. You have one functional group, carboxylic acid functional group, carboxylic acid functional group, so the functionality is equals to 2. Here you have dialcohol, which is ethylene glycol. It has one functional two functional group, OH, OH, so 2 functional group. It means that the functionality is equals to 2. And you remember we said for polymerization, the functionality must be greater than or equals to 2. So this one satisfied the condition. This monomer also satisfied this condition. So we are expecting to get a polymer. But how does the polymer formed? The first thing is the condensation reaction will happen, which means that the OH from here, the hydrogen from here, and then OH from here will be eliminated to form water, and this one and this unit will join together to form a dimer. So when you look at this product, it has alcohol here and it has acid group here. So this acid group can react with this alcohol, and this alcohol group can react with this acid. So if you look at the next step, the dimer, which is this dimer, can react with the alcohol. So at this point, you can also connect those 2 points with the elimination of water. So water can be eliminated. So once water is eliminated, we will form what? A trimer. Now when you look at this trimer, that is 3 units, you have at this end you have OH group, and at this end you have what? OH group. So which means that there is going to be reaction at this group at this end, and there is going to be another reaction at this end. So it means that since you have the 2 ends of the monomer are active, if you add them together, you end up with 2 active monomer terminal functional groups at the 2 ends, and this will continue until you get a polymer. So you start with the 2 monomers, you get dimer, and the dimer will react with another monomer to give you what? Trimer. This trimer has a functional group here, it has a functional group. It reacts with another monomer to give us tetramer, and tetramer will also have 2 functional groups at the 2 ends. It will react with another monomer to give pentamer. Pentamer continue, hexamer, until you get a long chain, and that long chain is called a polymer. So in summary, here, if the functionality is equal to 2 plus functionality is equal to 2, you end up with what? A polymer. So the reaction will continue until it becomes a long chain. So basically, what we have at the end is we are going to have multi-steps reaction leading to the formation of a linear chain called a polymer. And because the polymer is formed, we call the reaction is called condensation polymerization. Where polymer is not formed, we say it is condensation reaction. So in summary, to represent that reaction, we take n number of monomer, which could be 100 or could be 1000, with the n monomer of the second, the n number of the second monomer. Since the 2 of them have 2 functionality, F is equals to 2, F is equals to 2, it means that the 2 will react to form a polymer. So you end up with a polymer chain, and instead of writing a long chain, we put it in the bracket, as we have seen in chapter 5, where the repeating unit is put into the bracket, and then you have n to indicate the number of repeating unit, and this gives you the amount of water that will be eliminated during the reaction. So in this case, if functionality is equal to 2 plus functionality is equal to 2, we end up with a polymer, and because of that, we call it condensation polymerization. It is condensation because small molecule is eliminated, and the polymer is going to be a linear polymer. You remember in chapter 5, we discussed about different structures of the polymer. We could have linear polymer, branch polymer, or cross-linked polymer. So if you have functionality equals to 2 plus functionality is equals to 2, you end up with a linear polymer. Now, when do we get a branch polymer? Branch polymer is when we have a situation where we have functionality is equals to 3. For example, we have 3 alcohols here, 1, 2, 3. So F is equals to 3. And here we have 2 acid group, 1 acid, the second one, so the functionality is equals to 2. So here the situation is F is equals to 3 plus F is equals to 2. This will definitely give us a polymer because, as we said, for polymerization, functionality must be greater than or equals to 2. This is more than 2, and this is equal to 2. So this is going to give a polymer. So if you have 3 plus 2, you end up with a polymer. It is condensation polymerization, but it's going to give what? A branched polymer. It's going to give a branched polymer. If you have 2 plus 2, you end up with what? Linear polymer. Now, in some cases, you could end up with cross-linked polymer. And a specific example of that is the phenol. you remember the phenol is a special case. We say phenol, formaldehyde, and phosgene are special cases when we talk about functionality. So for phenol, functionality is equal to 3, and for formaldehyde, functionality is equal to 2. So if you have F is equal to 3 plus F is equal to 2, is going to give a branched polymer. But for this case, it gives a cross-link polymer. So this is one of reaction that leads to a cross-link. And this reaction, you are going to do this, is going to be part of polymerization of phenol formaldehyde, phenol with formaldehyde to form phenol formaldehyde resin, which we call bakelite plastics. This is part of the experiment you are going to do, inshallah, if we resume before the final. Now, you don't have to worry about the structure, but all you need to know, remember that this one, phenol, the functionality is equal to 3, phenol, formaldehyde functionality is equal to 2. So if you combine phenol with formaldehyde, you end up with a cross-link polymer, and the reaction is called condensation polymerization because it involves reaction of functional groups, which leads to elimination of small molecules. Now, to summarize, we said for polymerization, functionality of each monomer must be greater than or equals to 2. So if we have functionality equals to 1 and we react with another monomer whose functionality is equals to 1, we end up with no polymer. But if you have 1 and 2, no polymer. This one satisfied the condition, but this one does not satisfy the condition. So we end up with no polymer. But of course, there's going to be reaction, but this reaction will be two-step reaction, and this one will be one-step reaction. If it is a functionality equals to 1 plus 3, no polymer, because this one does not satisfy the condition, which states that functionality of each monomer must be greater than or equals to 2. Now, when you have 2 plus 2, then we end up with what? A polymer, and that polymer is linear. So we have a linear polymer. In some cases, if the functionality is equal to 2, you have only one monomer. For example, ethylene. Ethylene has one double bond. So it means the functionality is equal to 2. So ethylene can combine with another ethylene monomer to form a polymer, polyethylene, and that polymer is what? Is linear polymer because you are talking about functionality is equal to 2. Similarly, you can have ethylene glycol. Ethylene glycol contains 2 alcohol group. It can combine with another ethylene glycol to form polyethylene glycol, and that will give a linear polymer. If you have functionality is equals to 2 plus functionality equals to 3, it's going to give a branch polymer, but in some cases it also gives what? Cross-link polymer. Especially the example we gave is the reaction of phenol with formaldehyde. The functionality of phenol is 3, functionality of formaldehyde is 2, so it will end up with a cross-link polymer called a bakelite plastic. So in general, 2 plus 3 gives branch polymer, and in some cases it gives what? Cross-linked polymer. Now this brings us to the next topic, which is some common condensation polymers. The polymers that are condensation polymers that are very common, especially the first example here we have polyethylene terephthalate, the one we use, the polymer that is used for bottled water. Bottled water is PET, polyethylene terephthalate. It is formed from the reaction of terephthalic acid with ethylene glycol. So you have functionality 2 here, 1 functional group, 1 functional group. So you have functionality 2 plus ethylene glycol, which is it has 2 alcohol groups, so functionality is equal to 2. 2 plus 2 will give you a polymer, and it is called condensation polymerization. Polyethylene terephthalate is ethylene glycol is the antifreeze that we use in the car radiator, and it is produced in Saudi United, one of the SABIC affiliates. Another example is adipic acid and 1,6-hexamethylene-diamine or 1,6-diaminohexane. Here you have two functional group, carboxylic acid, and here you have diamine, amine and amine. This will give nylon 6,6. We discussed about the naming of the polymer, how we get 666 represent the first 6 represent the number of carbon between the two nitrogen, and the second 6 represent the remaining carbon. So here you have 1, 2, and then you have 4 in the middle, which is what? 2 plus 4 will give you what? 6. So this is called nylon. You are going to do this experiment in the lab, but in the lab you are going to use cibaquel chloride, which is the acid chloride of adipic acid. Instead of hydroxyl group, you have Cl here, you have Cl here, because the reaction is faster with cibaquel chloride. So you combine it with diamine, and then you get nylon 6,6. This is part of the experiment that will be conducted hopefully in the lab. The last one is phosgene with reaction of phosgene with bisphenol A. We have to produce polycarbonate. Polycarbonate, it is transparent polymer that is produced in Saudi Cayenne. It is used in many applications to replace glass. For example, the headlight of our car, some of the window of aircraft. Any application where transparency is required, you can use polycarbonate. We remember this is a special case monomer. The functionality is equal to 2, and here it has two functional groups, OH, OH. So the functionality is equal to 2. Functionality 2 plus 2 will give you a linear polymer, which we call polycarbonate. But most of the industry, especially in Saudi Cayenne, phosgene is a very dangerous chemical. So in most cases, to reduce the risk of phosgene, most of the company use diphenyl carbonate instead of phosgene. For example, in Saudi Cayenne, they use diphenyl carbonate, which is safer than phosgene. But of course, it's going to produce, if you use phosgene, the byproduct is HCl. HCl is an acid. You can easily remove it from the product. But when you use diphenyl carbonate, you end up with a phenol, which is very difficult to remove. In most cases, you need high vacuum to remove phenol from the product. So these are the three major common condensation polymers. Now, this slide shows a typical example of questions that you will encounter in this course. For example, you have monomer, for example, A and B, or sometimes you have only one. You want to know whether it's going to form polymer. Will it form polymer, yes or no? If yes, what type of polymer? Is it linear, branch, or cross-link? Now, before we go into this, you remember that functionality, we have three categories of functionality, either in terms of a double bond. If you have one carbon-carbon double bond, functionality is equal to 2. Or two carbon double bond, functionality equals to 4. Then the second category of functionality is the number of functional group. The number of functional group, if a molecule has one functional group, it means functionality is equals to 1. If it has 2, functionality equals to 2. The last category is the special case, and this special case, I gave you only 3 examples: phenol, formaldehyde, and phosgene. Phenol has functionality equals to 3, formaldehyde has functionality equals to 2, and phosgene has functionality equals to 2. So this functionality, you need to remember them. And once we identify the functionality, then we can predict whether it's going to give, the reaction will give a polymer or not. And you remember that for polymerization, functionality must be equal or greater than 2. Now, the last one, which is if it forms a polymer, linear polymers are formed from functionality monomers that are functionality equals to 2. If you have more than 2, it could be branch or cross-linked. Now, having this in your mind, let's start with the first one. The first one is phenol with formaldehyde. These two are special cases. And if you remember, we said the functionality of phenol is equal to 3 because it can react at this point, and also at this point. So functionality equals to 3. Formaldehyde is also a special case. Functionality is equal to 2. And you remember that we said for reaction of formaldehyde, since you have 3, this satisfies the condition, this one satisfies the condition, it means you are going to get a polymer. So it's going to give you a polymer. And the polymer, of course, it will be a cross-linked polymer, because remember that reaction of phenol with formaldehyde will give a bakelite plastic, and that bakelite plastic is a thermoset, which is a cross-linked polymer. Now let's look at the second one. The second one is propylene. It has a double bond, one double bond. Remember, one double bond means functionality is equals to 2. So here we have functionality is equals to 2. So if your functionality is equals to 2, it will react with itself. The monomer will react with other monomers, and you end up with what? A polymer. So if you have propylene, you end up with what? Polypropylene. So this will also give a polymer. And of course, if you have only 2, then it's going to give you a linear polymer. So this is similar to 2 plus 2. Now let's look at this one. This one has a benzene ring, and we said we don't count the number of double bond in benzene ring because the benzene ring is very stable and there's no reaction on the benzene ring. And here there is no double bond. So it means it has no double bond available for polymerization. It has no functional group, and it is not a special case. So the functionality is what? 0. So if the functionality is 0, it means it will not form a polymer, and of course the last column will remain blank. Now we'll move to the next one. This one has 2 organic acid group, carboxylic acid group, one here and then the second one here. So the functionality is equals to 2. This one has 3 alcohol group, OH, OH, OH. So it 3, so its functionality is equals to 3. So if you have 2 plus 3, you end up with a polymer, and of course the polymer is a branched polymer. So 2 plus 3 will give you a branched polymer, but in the case of phenolformaldehyde, it gives a cross-linked polymer. The next one is diamine. You have functionality 1 amine group here, so the functionality is equals to 2. Here you have carboxylic acid group here, carboxylic acid group, so the functionality is equals to 2. 2 plus 2 will give a polymer, and of course the polymer is a linear chain polymer. Now when you look at this one is also a propylene, but arranged differently. So the functionality is equals to 2 because it has 1 carbon-carbon double bond. This is hydrogen. Hydrogen has no functionality. It has no double bond. It has no functional group, and it is not a special case. So the functionality is 0. So 2 plus 0, this satisfies the condition, but since it is going to react with this, you end up with no polymer. Of course, in fact, this reaction is called addition reaction. You remember, one hydrogen will add to this, and the other hydrogen will add to this. So you move from a double bond to a single bond. Chapter 2, reaction of alkene. So this is no polymer, and the reaction is addition reaction. Now let's look at the last one. The last one has 1 functional group. This molecule has 1 functional group because it has only carboxylic acid. This one has alcohol group, so the functionality is equals to 1. So 1 plus 1, of course, will not give what? Will not give a polymer. this reaction, there's going to be reaction, or hydrogen from carboxylic acid group with OH from here will be eliminated as water, and you end up with an ester product, and the reaction is called condensation reaction, no polymer. So what is important here is you should be able to identify the functionality of a molecule, and you should be able to predict whether the reaction will give a polymer or not. And remember that functionality can either be in terms of a double bond, or in terms of a number of functional group, or a special case. And this brings us to the end of part 1, part A of chapter 8. Our next lecture will be we'll be discussing about the second part of chapter 8, which is numerical problems, and these numerical problems will be covered in chapter B, part B of this class. So hopefully in the next video we're going to discuss about this part B, which is condensation polymerization. Thank you very much. You can view the videos, and if you have any question, please feel free to send your question on the Blackboard discussion forum, or you can send me an email, or we can discuss questions during the live session on Thursday, inshallah. Assalamu alaikum wa rahmatullah.